Okay, so let us continue with the second session today, or this afternoon. It's Professor Adolfo Guillot. Probably all of you know much more than me. He's going to talk about uniformizable foliated projective structures along singular foliations.
Thank you, Beatriz. Thank you very much for being here. Thank you for the invitation. I'm very happy to be here sharing this mathematics with you. So I will talk about foliations by curves on compact manifolds, holomorphic foliations. And I will talk about some particular structures along the leaves of this foliation. And it's related to, but not exactly what Ilyashenko told us about simultaneous uniformization. But it's closely related. So let me telling you the kind of structures that I will put in the leaves of my foliation. So for the time being, I will talk about just curves, complex curves. And I will talk about affine and projective structures. So if you have a complex curve, you can, compact or not non-compact, doesn't matter, you can consider the following object. You can consider the possibility of giving it an atlas of charts, taking values in the Riemann sphere, in the projective line, such that when you take two different charts, their difference is given by a Möbius transformation. So a projective structure on a curve with a given complex structure is just an atlas taking values in the projective line and changes of coordinates given by Möbius transformation. So everything that is local for Möbius transformation makes sense in your curve. Okay? This is projective, and you can also, this is a projective structure. You can also talk about affine structures where you have a curve and you take charts with values in the complex plane. And if you have two different charts, their difference is given by an affine map. Okay, so this is a particular case of a projective structure. And this is an affine structure. So everything that makes sense in affine geometry, for example, being the line, will make sense with a projective structure. Everything that makes sense that is invariant under Möbius transformation, for example, being a line or an arc of a circle, will make sense here. Okay, so see in this geometry we have hyperbolic geometry. That is, you restrict when the parameters when A, B, C, and D are real. And you also have spherical geometry. And within the affine, you have Euclidean geometry. So projective geometry in one dimension encompasses all these geometries, generalizes simultaneously all of these geometries. So examples of projective structures on curves come from the uniformization theorem. So you have this very, very important historical theorem that tells you that if you take a curve, no matter which one, its universal cover can be identified to the upper half plane. And equivalently, you have a group acting on the upper half plane by projective Möbius transformations with real coefficients, such that the quotient is the curve you started with. Since you are acting by Möbius transformations, it means that you have a projective structure on the curve. If I have a point, I can take one of the local inverses as charts, and if I have two charts, it means that I have two different images. But since I go from one to the other by a transformation belonging to my group, I have a projective structure on my curve. This is a sort of expensive way to produce projective structures. There are cheaper ways, but this is a very, very important source. And I will distinguish two kinds will be a very special kind of projective structure. And I will say that a projective structure is uniformizable. So a projective structure on a curve C is uniformizable if C, together with its projective structure, is the quotient of omega, some domain in P1 under the action of a group acting by Möbius transformations. So this is an example of uniformizable projective structure. There are other sorts of uniformizable projective structures. And I will say that this is strongly uniformizable if this omega is simply connected. So this is not what Ilyashenko called strongly uniformizable. I'm talking about uniformizability of projective structures on curves. Okay? So no foliation for the time being, just curves, complex curves, one-dimensional curves. So strongly uniformizable, it means you're the quotient, strongly if you're the quotient of a simply connected set. Okay? For example, the upper half plane is strongly uniformizable, but for example, there's this Schottky uniformization where you quotient the complement of a Cantor set in the projective line, and you obtain a compact curve together with a projective structure that would be uniformizable in this terminology, but not strongly uniformizable. Okay? So, okay. So I'll stop there. So I will not, yes, there's another way. When I have an affine, no, I'll say this later. Okay, so I will talk about foliations. And what I mean by a foliation, I will always take M. So these are curves. And I will abandon the curves, and I will talk about foliations on manifolds. So I will take M, in general, would be compact complex manifold. And I will consider F a foliation by curves on M. And this foliation is given, so I have my manifold, and I want this n-dimensional manifold, and I want to cover it by some open sets, Ui, such that on each one of the open sets, I have a vector field, Zi, holomorphic vector field, with singular set of codimension at least 2, such that when 2 of my domains intersect, they are the same up to some multiplicative function. So there's this function defined in the intersection of the domains, and it's nowhere, it's non-vanishing. So you cannot really glue the differential equations because you're changing the parameter here, but you can glue the orbits of the differential equations, and you get globally a foliation, and you have some singular points. The singular points are the singular points of the vector field Zi. So for example, the linear part of a foliation, it's not well defined because I don't have one vector field defining it, but it's well defined up to multiplication by a constant, and that makes sense with this definition. Okay? So I can not really say what the eigenvalue is, but the ratio of two eigenvalues, that I can say. Okay? So these are compact manifolds, and then the foliation, we have some singular points, and then we'll have some singular points, and then we have some integral curves. These are Riemann surfaces, complex curves. So each one of them, we can apply the uniformization theorem for each one of them, and so for one curve, uniformization works very well, but for families of curves, especially for holomorphic families of curves, that's another story. That's what Ilyashenko was telling us about. But let me state a theorem So this is, a lot of people thought about the uniformization of the leaves of a foliation. Let me mention Alberto Berkowski, Alberto Candel, and then there are some works in the singular setting by Gomez-Mont and Candel. And the theorem I want to tell you about is a theorem by Alcides Celins Neto. Which says the following. Take a foliation F by curves on the projective space of dimension n, and suppose that the singularities are non-degenerate. Okay, so this is a generic condition. And suppose also that the degree of F, I will tell you what this is at least 2. So you have your projective space, Pn. You have your foliation by curves, defined as I just told you. And when you take a hyperplane, a generic hyperplane, most solutions will traverse it, but it will be tangent to it at a certain number of points, and this number of points does not depend on the generic hyperplane that I chose, and this is the degree of the foliation on the projective space. Okay? So suppose the degree is greater or equal than 2, then two things happen. First, all the leaves are uniformized by the disk. So the uniformization, you have curves that are uniformized by the disk, by the complex plane, the complex line, or by the Riemann sphere. So all the leaves are uniformized by the disk under this assumption. And also the uniformizations vary continuously. One way to say this would be each uniformization gives you a metric along the leaves, and this metric varies continuously. Okay? So, because you have to normalize something for this uniformization to be unique, but the metric is independent of these choices. So everything, it seems that all the objects here are holomorphic, and we're only getting continuous variation. So the question is, can we change the type of uniformizing domain in order to get something that varies holomorphically in this setting? Okay, so I will give you a setting where this can be, where I can give us a precise statement for this. Okay, and that will be the setting of foliated projective structures. Okay, because you see, so you can uniformize by the upper half plane, but you also can uniformize by, say, the domains associated to quasi-Fuchsian groups. So you can uniformize by the disk, but also by quasi-Fuchsian groups, and this uniformization will uniformize the same complex structure, but will give you a different projective structure on the curve. So it's with projective structures that I want to play. So let me tell you what this is foliated. So we call these foliated projective structures. We didn't invent them. They existed before, but we sort of studied them and called them foliated projective structures. Okay, so let me tell you what that is. So you have a compact manifold. You have a foliation by curves. And a foliated projective structure will be, you take a leaf, and you give a leaf, the leaf is a complex curve, and you can give it a projective structure to this leaf. And what a foliated projective structure is give a projective structure to each curve, but such that they vary holomorphically. Okay? One way to say that is that away from the singularities of F, you have charts. So your foliated projective structure will have, so you have your chart, you have your manifold, your foliation, and away from the singular points, you have charts taking values in P1. If your manifold is of dimension n, you have charts taking values in P1 times z, such that the changes of coordinates are of the form z, t, a parameter in the here, will be mapped to a of t, z plus b of t, c of t, z plus d of t, some function phi of t. Okay? So this is the second part is what gives you a foliated chart. So the foliation is given by the levels of the second factor, and the fact that in your changes of coordinates, you only permute them, tells you that you have a foliation. You permute the level sets. But the thing here is you have a projective coordinate, and you want it to be preserved by changes of coordinates.
Are these functions holomorphic?
Yes, they are. Yes, this is an atlas holomorphic. And this gives you, so this gives you projective structures on each leaf, and they vary holomorphically from leaf to leaf because these functions vary holomorphically. So that's what we call a foliated projective structure. Okay, so the first question is, do these objects exist? Okay, so probably it's too much to ask. And the thing is, they do exist. They exist more often than one would expect. They don't exist always. Projective structures on curves always exist. But for given a manifold and a foliation, a compact manifold and a foliation, they do not always exist. Let me show you that they do indeed exist for foliations on Pn. Projective space. So you have your projective space, again, a foliation by curves. And in fact, it's not difficult to see that all the foliations on Pn, a foliation of Pn of degree d comes actually from a vector field in Cn plus 1, a vector field homogeneous of degree d, so given by homogeneous polynomials of degree d, the degree of the foliation. So, and the fact that they are homogeneous tells you that I have this radial directions, and the fact that it is homogeneous tells you that if I take an integral curve of the vector field, which will, so the foliation is produced by the projection of the integral curves of the vector field here, and all the foliations on the projective space, or projective space can be constructed in this way. And the thing is that if I take my solution and then I make a homotopy of that solution, I will get another curve here, and the homogeneity will tell you that this will be still a solution of the equation. I just have to parameterize it uniformly at a different speed. Okay? But what I'm telling you is that the homotopy will map the affine class of this parametrization to the affine class of this parametrization. So when I project them, the vector field will give me along each integral curve an affine coordinate, an affine structure, and in particular, a projective one. Okay? So every vector field on Pn, every foliation on Pn, has a foliated projective structure. Actually, you have many of them. You have an affine space of dimension degree d on Pn, n plus 2d minus 2 chooses n. So this is the dimension of the space of foliated projective structures on Pn. Okay? So you have many, many foliated projective structures. For example, you have foliated projective structures for every foliation on a generic hypersurface of P3. On every Calabi-Yau manifold, every foliation has a foliated projective structure. Say on the product of P1 with any curve, have a foliated projective structure. So they are very, very common. They are more common than we expected. Okay, so there are many foliations that admit a foliated projective structure. And I will say, so these are foliated projective structures, those are examples of foliated projective structures. And let me say that a foliated projective structure is uniformizable or strongly uniformizable if all its leaves are. Okay, so every leaf of the foliation has I have a foliated projective structure, and if the projective structure on every leaf is uniformizable, if it can be produced as the quotient of a domain under the action of a group, if this happens for every leaf, I will say that the foliated projective structure is uniformizable. If the domain uniformizing every leaf is moreover simply connected, I will say that the foliation is strongly uniformizable. Okay, so this is the key definition. Is it clear?
This is the theorem.
So this is a theorem by Alcides. I'm not, so there's no theorem yet. So this is the definition. I'm telling you what uniformizable or strongly uniformizable foliated projective structure is. So that's the definition. So what we did was we have been studying these objects for some time, and we have been studying the obstructions or so foliated projective structures are quite common, but uniformizable foliated projective structures turn out to be very rare. And the singular points impose very restrictive conditions for the existence of these structures. So let me give you two corollaries of our results, of our work. The one is in the context of Linz-Netto's theorem. So as a corollary of our work, we have the following. So you take, again, F, a foliation on Pn, non-degenerate singularities. Admitting a strongly uniformizable foliated projective structure. Okay? Then the degree of your foliation is either 0 or 1. So you have a degree 2 foliation. You will never get a uniformizable foliated projective structures. You cannot uniformize these. You cannot give a projective structure such that every curve is a quotient of a simply connected domain. Okay? If the degree of your foliation is 0, then you have your foliation is given by the lines through a point in projective space. There, each line is a line, it's a projective line, and this is the complement of a point in a projective line, which inherits a projective structure. And if the degree of your foliation is 1, then in some affine chart, you find a linear vector field. Then F is given by a linear vector field. A globally defined vector field. And then you have your parametrizations defined in all of C. So you have a vector field on a compact manifold. The solutions can be parametrized by C. And then this will give you the uniformization by the simply connected domain. In degrees 1, 0, and 1. But from degree 2 onwards, you cannot have these projective structures. So this is one corollary. Let me give you another one that's related to what Ilyashenko was saying. Suppose that you have a surface, complex compact surface, that fibers over a curve, a compact curve, and that the fibers are connected. Most of the fibers are connected, curves, with some genus, and you probably have some fibers that have some points where you do not have, where you have some singularities, say with local first integral ZW. Okay, are the ones that Ilyashenko was telling us about. Okay, so this is in particular a foliation. So I have this, this is one of the examples. So I have my surface, and my surface fibers over a curve. Doesn't need to be a compact curve. And this is all compact. And you have a foliation given by the fibers with singularities given by these Morse points. And as a corollary of what we're doing, say, suppose that you give this foliation a projective structure, a foliated projective structure. This is on each curve. I will choose a projective structure that varies holomorphically in the sense I just said. And suppose, moreover, that at the punctures here, the projective structure makes the punctures parabolic. So this is a feature of the projective structure. So by parabolic punctures, I mean that every puncture here is, so this is just, the complex structure is that of a disk without a point. But the projective structure is given by the quotient of the upper half plane by a translation. So these are parabolic punctures. These are the ones you obtain when you use the uniformization theorem for higher genus. You obtain parabolic punctures, both for Fuchsian groups and for quasi-Fuchsian groups. So suppose that you have a foliated projective structure here, and that at the singular points you have parabolic punctures.
And the bottom surface is compact.
It's compact, yes. So everything will be for ambient, compact ambient manifolds. Then your fibers are constant in the Teichmüller space. The complex structure in your fibers does not move. That's the conclusion. Okay. Okay. So these are two consequences of our results. I will state them now. But I will make a parenthesis now and tell you a relation with Ilyashenko's notion of uniformization. Suppose that you have a strong, this is, okay. See. Then the fibers, so if you have, so most fibers are compact curves. They have all the same genus. Most of them will have the same genus. So when you have that, in principle, the fiber moves in the Teichmüller space of genus 2 curves, or genus 3 curves. The conclusion of the theorem is that this fiber does not move. It's constant. It's always the same fiber. So you cannot. So the fiber varies. You cannot give a foliated projective structure with parabolic punctures. So in particular, if there are no singular points, and you have what is called a Kodaira fibration, then you do not have. If the fiber moves, you do not have a foliated projective structure. Okay, so let me just tell one thing. So if you have a strongly, in this sense, if you have a strongly uniformizable foliated projective structure on a manifold, and you have a transversal, and you glue abstractly the universal covers of this transversal. Then if you fix some data here, you can build a developing map, and each fiber will be mapped. And this developing map, if your transversal here is T, here you have your covering, collection of covering spaces, the covering tube, and you have a developing map taking values in P1 cross T, holomorphic, mapping each leaf to its universal cover. So each universal cover into the disk that uniformizes it. And this is where these strongly uniformizable foliated projective structures are related to the simultaneous uniformizability described by Ilyashenko. So it's in a sense, you have, for all the transversals, you have these mappings, and you have, moreover, a compatibility of the projective structure inherited by these maps along all transversals. So this allows you to in some sense, forget about the transversals, because you have compatibility among them. Okay. So questions so far? Aquí? Okay, so what I said is, so I didn't tell you what this developing map is, but when you have a projective structure in a curve, and you take its universal covering, you inherit a universal covering, projective structure on the covering. So this will have a globally defined chart. So charts are local, but if you are simply connected, they will be global. So this global chart is this D. This D, for a generic projective structure, can be very complicated, can be wrapping infinitely many times around the sphere. But in these strongly uniformizable foliated projective structures, this global chart will be injective. That's another way to characterize them. So if I have a strongly uniformizable foliated projective structure, Ilyashenko explained us how to glue the universal coverings together. Here is my foliation. Here I just took the same transversal and glue. So I have the leaf here, and I have here the universal cover of the leaf with this point. And then this developing maps, if you fix some data, will give a holomorphic map into P1 cross T. So this cylinder or this covering tube will embed into P1 cross T, and so it will be simultaneously uniformizable in the sense of Ilyashenko. Okay. So There is another way to describe, to say what a foliated projective structure is. So you can do it with charts, but there's another way, more analytic, and is the following. So a foliated projective structure can be described by the following object. We'll have some object that will assign a vector field tangent, this is local, and to a vector field tangent to your foliation. So the foliated projective structure will be given by this object, vector field tangent to your foliation. You will assign a function. This is all holomorphic. So to your vector field tangent to the foliation, you will associate a function defined in the same domain as the vector field is, that is subject to the following rule. It's the same. A function, C, that it's a function of Z. So it's a function that depends on Z. So I will write, so this function will be, it depends on Z. So different vector fields tangent to the foliation will give you different functions. And that's why I write C of Z.
On the right, Z is a coordinate, and on the left it is a vector field.
No, this is all vector fields on your manifold. So this is U, and this is an open set, and you have a vector field, Z, defined on U. C is a vector field, and I will have a function. This is a function defined on U, but that depends on my vector field. So each time I give a vector field tangent to the foliation, I will gain a function on U. And this function will satisfy the following rule. So if I multiply, all the vector fields that are tangent to the foliation can be deduced from one another by multiplying by a function. So I will tell you what the effect on this function, on this object multiplying by a function is. It's a bit complicated, but I will explain it right now. Okay, so it satisfies this. So so the f, you extract it with a square, and then you add some terms. This is some sort of modified Leibniz rule, and this is a projective connection. So a foliated projective structure can be given by a foliated projective connection. What is it? It's an object that, to a vector field tangent to the foliation, associates a function satisfying this rule. Okay? So it looks a bit strange. Let me tell you what it is on C, on P1. If I take my coordinate Z, that's my vector field. So what's the relation? How can I read the projective structure from this expression? So I will look for the vector fields along which this vanishes. So if I have a vector field and this object vanishes, the coordinates associated to that vector field will be my projective coordinates. Okay? As an example, if on P1, this dz gives me a projective coordinate, and the other vector fields for which this expression vanishes are the vector fields of the form az squared plus bz plus c, a, b, and c complex numbers, such that AC, such that the determinant is 0. So these vector fields correspond, they have only these vector fields live on P1. They have only 1, 0. And the complement is just an affine chart where you have an affine coordinate. So this projective connection it's related to the properties of the Schwarzian derivative. And when I put it here on P1 for my standard projective structure, and I take the projective structure given by my coordinate z, just the other ones, the vector fields such that when I multiply, so if I have this, that this expression, this object gives me the 0 function when I plug in the vector field d over dz. When I plug in any function, multiply by any function, if my new function is still 0, is because my vector field has this form. That means that its solutions give me the other projective coordinates. It's a way to identify projective coordinates in an analytic way.
Adolfo, may I ask you to explain the formula for Xi of Fz?
So let me tell you a bit different. In the affine case, you know that if you have a coordinate and you have a vector field, let me suppose that I have a curve. On a curve, I have a connection. So I only have one vector field. So if I differentiate z over z, I will get some Christoffel symbol times z. But the Christoffel symbol will depend on z, and then will multiply. Okay, so you can think of an affine connection on a curve as something that to a vector field, z, associates a function, its Christoffel symbol, that satisfies the following rule. So this is the rule. You can forget about the affine connection and say only that an affine structure on a curve will be flat because its curvature will be 0, is an object that to a vector field associates a function, its Christoffel symbol, in such a way that when you multiply your vector field by a function, you will obtain two terms. One, just take out the function, and another, just derivate the function by your vector field. This is the same, but for a projective connection, not for an affine one. And this is related to the properties of the Schwarzian derivative. And it's a bit complicated, but if I have the projective connection that vanishes along this vector field, it will vanish along the quadratic vector fields with vanishing discriminant, which are associated to so these will vanish at one point in P1, and its solutions will give the other projective coordinates. So you will obtain projective coordinates from the vector fields where this vanishes. Okay. So this object. So let me erase this part. Okay. That's the analogy with affine structures. An affine structure is given by a connection. The connection has a Christoffel symbol that satisfies this rule. You can forget about the connection and only think that the connection is something that to a vector field associates it a function, its Christoffel symbol, and that it varies in this way. Okay, so a foliated projective structure will separate the singularities of the foliation in two types. One, or foliation, one of them I will call parabolic. Parabolic means that if I take a vector field, so if I take a vector field, so this is a singular point, so I take a local vector field defining the foliation, and P is a singular point. So it is only in this setting that I define, it's an attribute of singular points. So this is a function, and I can evaluate it in P, and if this is 0, okay? And non-parabolic, so I have still a singular point if, okay? So if my foliation is given by a vector field, and this same vector field gives me the projective structure, its parameterized solutions give me the projective structure, then I will be the parabolic vector field. The singularity will be parabolic. If P is a non-degenerate parabolic, so non-degenerate is a property of the foliation. Parabolic is a property of the foliated projective structure. And if I have a curve that passes through my singular point as a paratrix, an invariant curve, then along this curve, this puncture will be parabolic in the sense I just described. Okay, and that's why I put this name. Okay, so if you let us only consider non-degenerate vector fields from now on. So parabolic means that the curves that go through the point, when they pass through the point, they get a puncture, and they have a projective structure, and this projective structure will be parabolic. They will be given locally by, say, the translation of an upper half plane under translation. Okay? But it's something that can be read directly from the projective Christoffel symbol. Okay? I will leave that because, so let me state two theorems. So M compact manifold, F foliation by curves on M. You have a foliated, a strongly uniformizable foliated, no, yes, foliated projective structure. Suppose that you have a point P, a singular point of F that is non-parabolic with respect, in that sense, with respect to your foliated projective structures. Then, if your manifold has dimension n, you will find, so this algebraic projective manifold. So you will find a projective analytic space of dimension n minus 1 and a dominant map, a dominant meromorphic map. So the fibers will be one-dimensional, the generic fibers will be one-dimensional, and they will contain the leaves of the foliation, which will be rational curves, copies of P1. So if you have just one singular point of the foliation that has this property of being non-parabolic, then you have, in a suitable sense, a first integral of your foliation. So the foliation is given essentially by, it's a fibration, it's a ruled, you have a ruling, you have a fibration by rational curves. essentially. Okay, so one non-parabolic, non-degenerate, did I say? Non-degenerate. So just one tells you everything about the foliation. Okay? So here M, again, so this is one result, then compact manifold, F, again, foliation by curves plus a foliated structures. Suppose that all singularities are non-degenerate. This is that the linear part of the vector field defining them has no zero eigenvalue, and that they are parabolic. Okay, so either you have one singularity that is non-parabolic, or else all your singularities will be parabolic. And when all the singularities are parabolic, I will not give the most general result, but so what we will have is a restriction, a topological restriction concerning the manifold and some bundles associated to the foliation, like in Pepe's talk yesterday. So if the dimension of M is even, we have that the first Chern class to the power 2k of the tangent line bundle of the foliation is 0. And so we have more general formulas, but if you have this, then this is the same normal bundle that is a virtual bundle, but it has Chern classes 0. Okay, so we have more general formulas, but these ones are good. So the result, especially this one, is especially restrictive on even dimensions. So in all cases, we have a lot of information about our foliation. So it tells you how restrictive the condition. So in the second, we really don't need the uniformizability. We only need the parabolicity of the singular points. And here we do need the strongly uniformizable foliated projective structure. So questions about the statements? Okay, so so the best thing that can happen when you have in a manifold of dimension n, when you have a differential equation, the best thing that can happen is that you have n minus 1 independent functions that are constant along the leaves of your foliation. That's usually called completely integrable foliation. So you have enough first integrals. So you have the energy, and you have the momentum, and you have that. So you have enough of them. Your behavior ends up being very simple because each time you add one constant function, one function that is constant along the leaves, you pass from an n-dimensional thing to a family of some systems of lower dimension, which are in principle easier to understand. So what I'm saying here is that in an appropriate class, which is that of algebraic manifolds, this is exactly what happens. You have some space, and you have a lot of functions that are constant along your leaves. So it's the best possible, it's the dynamically most boring situation. So,
does n have some property, or?
No, it's just it's like you have an algebraic, so it's an algebraic space, analytic space. So you can lower it to Keller, and then this will be Keller. And yeah. Okay, so 2 words here. For this first result, we have a result about, for not strongly uniformizable, but just for uniformizable foliations, we have, with this condition of non-degenerate and non-parabolic, we have a normal form theorem that takes a especially strong form for the case where you have strongly uniformizable. So we have local normal forms that tell you that you have strongly uniformizable singular point. So it's strongly uniformizable ambient manifold, a non-degenerate, non-parabolic singular point. Then your foliation is given locally by a vector field of the form so you have just plus 1s and minus 1s as eigenvalues. And moreover, the Christoffel symbol for this foliation, which is non-zero, is the constant minus 1/2. So we have a normal form theorem that covers this situation. And then you have many first integrals here, and then you can globalize them using a result by Gomez-Monte to the whole ambient manifold. For the second result, when you have a projective structure on a curve, you can associate to it a Riccati foliation. It's usually called the graph of the projective structure. And this construction works well also in the foliated setting. You can construct a manifold, has one dimension more than the manifold we're in. We have another foliation, so this manifold will be a rule, and we'll have a ruling, a fibration by rational curves over our original manifold. And we have another foliation by curves whose geometry is related to the geometry of the projective structure, of the foliated projective structure. And if in that foliation we apply the bound-bot theorems that Pepe told us about yesterday, we will have some results that concern this higher manifold. But you can interpret this Chern classes of that manifold in terms of the Chern classes that live in the manifold that interests you, and you obtain these sorts of functions. And the fact is that the singularities you gain from non-degenerate singularities will not contribute if all of them are parabolic. So you don't see contribution from the singularities here. So we get more general expressions. It depends on the function you plug into the bound-bot theorem, but they always have the tangent bundle appearing to some even power. So they are not bound-bot. The bound-bot theorem only gives you information for the normal bundle, but here we have the geometry along the leaves gives us restrictions here. Okay, so just to finish, so coming back to my example here. So in this case, you can apply the second theorem, and the second theorem will give you, in this context, that if you have, you have to understand the case where there's one non-parabolic point that will lead you to degree 0. And when you have parabolic points, you can use the second theorem. And the second theorem will tell you that in even dimension, will tell you that 1 minus d to the n equals 0. So you can read the tangent is 1 minus d times the hyperplane class. And this is in the even case, and in the odd case, you will have 1 minus d to the n minus 1 times n plus d directly equals 0. So, so the only chance when d is not 0 is that d equals 1, just by using the second result in the absence of non-parabolic points. And then, when you are in this situation, and even dimension, it turns out that if you add some local hypotheses that are satisfied in my second example, you can conclude that this is not the foliation is not of general type. That is, that it can be treated within a potential classification that does not exist in higher dimension, only exists in dimension 2. But in principle, it is in the part that we can understand. And it's a program that was developed in dimension 2 by Brunella, Mendes, and McQuillan. And it will tell you, in this case, that this foliation is of Kodaira dimension less than 2, and that implies that the fibers are constant. Okay, so this is a consequence. You can control a lot of things from the foliation. So that the foliation is not of general type. Okay, so I will stop here. Thank you very much.
So are there more questions or comments? I think that there have been some of them during the talks, or there is people in Zoom. So there is someone that wants to ask something to Adolfo.
No, bueno. Okay.
In the chat, there's something. Okay, so we thank you.
Gracias.